Welcome back. In the previous lecture, we started graph theory, and after a few definitions, we proved the first theorem in graph theory, which stated that the sum of the degrees of all vertices is twice the number of edges, which is an even number. Then at the end of the lecture, we defined what are called directed graphs or digraphs. Now we can get a similar result for digraphs, which says that if you take the sum over all the out degrees of the vertices, right, the number of arcs going out of vertices, that must be equal to the number of arcs which are coming into the vertices, right, which is the number of arcs. This is kind of obvious, but still, if you want to give a formal argument, you just look at any vertex, you can see that if you look at any arc, you can see that it contributes 1 to the sum of its out degrees of its initial vertex, and 1 to the sum of n degrees of its ending vertex. So therefore, the result follows immediately. Now, in digraphs, we often allow loops. So what are loops? Loops are basically arcs which start and end in the same vertex. Like for example, if the vertex 1 has a loop there, it means that the arc 1 to 1 is there, right? So similarly, we have a loop at vertex 2 in this graph, but there are no loops on 3 and 4. So we have, this is often very useful in digraph. So we will allow that. Of course, we will look at many digraphs without loops, and we will usually try to be clear when we are using them. Now, the degree of a vertex is, of course, the sum of the in degree and out degree. Now, thus loops count as 2 for the degree of a vertex. Okay? So this is something which is important. So if you have a loop at a vertex, then that loop counts for 2 edges incident to that, right? As one as the outgoing edge and one as the incoming edge. So this is something that you should keep in mind. Now, the concepts of walks, paths, and cycle are very much similar to the case of undirected graphs, except that instead of edges, we are looking at directed edges, right, or arcs. Now, if for example v1, v2, vk is a directed walk, then what we know is that vi plus 1 is an arc for a very I less than k, right? So you are basically saying that instead of saying that vi plus 1 is an edge, we are saying that vi plus 1 is an arc. That means that the arc goes from vi to vi plus 1. Now, this is this says that there is a direction in which the movement can happen, right? So if you have a walk or a path from v1 to vk, it does not mean that there is a path from vk to v1, for example, right? This is different from the case of undirected graphs. Now, a directed walk in which no vertices are repeated is called a directed path, as just like we defined in the case of undirected graphs. And here is an example, right? You have a UV directed path. So what we have to notice is that the arcs are in the direction of the walk, right? So it always goes forward. I mean, for example, what I wanted to say is that, if you have let us say such a setting, 1, 2, and 3, and if these are the arcs, then there is no 1, 3 walk, right? This is not a 1, 3 path or walk, but in the undirected graph, this would have been a walk. Now, a directed cycle is, as in the previous case, if there is a UV walk or a UV path, you add the arc V to U, right? V to U, because U to V we are going, and then you have to go from V back to U. Then this cycle that we obtain is a directed cycle. Now, if you look at this graph above, you can see some directed cycles, right? For example, 1 to 3, 3 to 2, and 2 to 1 is a directed cycle, right? Similarly, 1 to 5, 5 to 4, 4 to 3, 3 to 2, and 2 to 1, right? This is another directed cycle. What about 1 to 5, 5 to 6, but 6 to 1 is not an arc, so therefore this is not a directed cycle, right? So this one is not a directed cycle, but on the other hand, this 1, 2, 3, right? 1, 3, 2 is a directed cycle. So these are the differences and similarities. Now we define what is called a functional digraph. So a digraph where with a vertex set V, that is, we will assume that it is finite for the time being, is a functional digraph if the out degree of every vertex is equal to 1. So every vertex has out degree exactly 1, then we say that the graph is a functional digraph. Now, why is it called functional digraph? Well, let us look at an example. So here is a functional digraph, right? So you have, if you look at any vertex, like 1, 2, 3, 4, 5, 6, 7, right? Each of them has exactly one outgoing edge. Okay, each vertex has exactly one outgoing edge. Now, this you can verify. It's true for every vertex. Every vertex has exactly one outgoing edge. Now, if we have such a digraph, then we can associate a function from the vertex at V to itself by defining the outgoing arrow as the function, right? Taking the starting vertex to the ending vertex, right? So this defines a function from vertex to its out neighbor, right? Because there is only one, so it's a unique out neighbor, therefore the function is well defined. So you can see the definition of the function that we have represented in this functional diagram as f of 1 is equal to 3, f of 2 is equal to 3, right? So 1 and 2 are mapped to 3. Similarly, 3, 5 and 7 are all mapped to 4. You can see that here, right? So you get 5, 3 and 7, right? All are mapped to 4. And similarly, you have the other vertices or the elements mapped to other vertices. So this defines a function, so therefore what we call is a functional diagram. So given any functional diagram, we have an associated function, right? And if you have a function on a finite set, you have an associated functional diagram. Now, a vertex of a functional digraph is said to be cyclic if V belongs to some cycle of the diagram. So if you notice this, you have seen some cycles, right? For example, there is a loop here, there is a cycle of length 2 here, there is a cycle of length 1, 2, 3, 4 here, right? So there were some cycles. Now, if your functional diagram have some cycles, look at the cycles and look at the vertices that are part of the cycle, like 4, 6, 7, 8, right? 12, 13, 14, right? These vertices are part of cycles. But on the other hand, 11 was not part of a cycle, right? 16 was not part of a cycle. 15 was not part of a cycle. So the vertices which are part of cycle are called cyclic vertices, okay, for functional diagrams. Now, if a vertex V belongs to some cycle, then we say it is a cyclic vertex. And in the previous example, we said that 14, 13, 12, 8, 7, 4, and 6 are cyclic vertices, and other vertices are not cyclic. So this is something that you can easily verify. Now, given a functional digraph, if it has a unique cyclic vertex, okay, which let us call R, then we call the digraph as a rooted tree. So given a functional digraph where there is exactly one vertex with a cycle, okay, then we call this as a rooted tree. And the root vertex where the cycle is present, that single vertex where there is a cycle, right? For example, here 7. That vertex R is called the root of the rooted tree. Now, in this example, you have the rooted tree with root 7, right? So this is something that you can look at more examples. So draw some examples and see what are the functional diagrams which are rooted trees and things like that. So you take some examples, try it out. Now a couple of homework questions. So first one is to define 5 different functions from the vertex at 1 to 12 to itself. Now once you define this function, you draw the corresponding functional diagrams. Okay, so for each function you define the corresponding functional digraph, and then try to study some properties of this. Can you see something about this? So then second part of the homework says that draw 2 functional digraphs, each on 8 vertices, 9 vertices, and 10 vertices. Okay, so for each of these graphs, you write the corresponding functions. So basically, you for each functional digraph that you make on 8 vertices, right? You write the corresponding functions, and then for the 2 on the 9 vertices, you do the same thing. Now, once you do all this thing, then the third question asks you to see if you can observe some interesting properties about the functional diagram. Okay? And if you find some properties, try to prove that. So whatever properties you can find, you should be able to find at least a few. Whatever you find, try to claim it and then write it down as a proof. Now, given the fourth question is that given a graph G, then every so this is not directed graph question. Okay? Then every closed walk of odd length contains an odd cycle. Okay, so given a graph G, show that every closed walk of odd length contains an odd cycle. Now, back to functional digraph. So if you look at functional digraph of permutation, because permutation is a function from a set to itself. Now, which is also a bijection, right? So now consider the permutation P, right? So here is an example given. So 1 is going to 7, 2 is going to 8, 3 goes to 4, 4 goes to 3, etc. Right? So once you have this permutation P, let us draw the functional digraph of P. Okay? So the functional digraph of P is like this. So 1 goes to 7, right? So 1 to 7. Then 7 goes to 5, so 7 to 5. And then 5 goes to 6. No, 5 goes to 10. So 5 to 10. And 10 goes to 1. For 10 to 1. Right? Similarly, 3 is going to 4, and 4 is going to 3. Right? And 2 going to 8, 8 going to 6, and 6 going back to 2. Similarly, 9 is mapped to itself, so you have a loop here. So you get this functional digraph of the permutation. Did you notice anything strange about this? I mean, with one example, it's not easy to say, but maybe you can look at a few more examples and try to verify what you see is indeed always the case. Now, so the observation is that the functional digraph of permutations is a collection of cycles. Okay? Means that there are no vertices which are not part of cycles, right? So all the vertices are cyclic vertices, and the functional diagram is basically a collection of cycles. There are no vertices which are feeding into the cycles, right? There is no outside vertex. Every vertex is part of some cycle. Now, further, inversing each arc of the digraph, right? So we get a functional digraph of the inverse of the associated permutation. Okay. Functional digraph of permutations. Now, the theorem formalizes, this observer, the first part of the observation. Let f goes from V to V be a bijection, right? Then the functional digraph of V is a disjoint union of directed cycles, right? So bijection from a set to itself is basically a permutation. So what we are saying is that the functional digraph of permutations are disjoint union of directed cycles. The proof is quite straightforward, but let us take a look. Now, what we know is that the function f that we are defining is a bijection, right? Which means that it is a 1, 1 and 1, 2, and therefore every element of the set V has a unique image and a unique pre-image, right? Because it's a function, it has a unique image, and it's a bijection, it has a unique pre-image, right? So which means that every vertex of the functional digraph has the 1 out degree, right? Out degree is equal to 1, and in degree is also equal to 1, right? So therefore, one outgoing edge and one incoming edge, precisely 1. Now, what does this say? So if a vertex has one incoming edge and one outgoing edge, right? Then it has the vertex has degree exactly 2, right? This vertex has degree 2 because one incoming and one outgoing, right? So the total degree of the vertex is 2. Now if every vertex, let's say in a graph, has degree 2, right? So you have a finite graph where every vertex has degree exactly 2, then we can see that the graph must decompose into cycles. Why is that? Maybe you should think about this. Okay, so if every vertex has degree exactly 2, the digraph decomposes, not necessarily digraph, the graph decomposes into cycles, disjoint cycles. Now, so why is this? So every vertex has degree 2, it must decompose into disjoint cycles because if you take, for example, let us say that because when you go into a vertex, right? You can also go out of it, right? So you keep on doing this because the degree is 2. Then eventually the graph is finite, means that you have to come back, right? You have to, because once you enter, if you don't take that edge, right? You are going out, you cannot go out. Then again, once you enter, you can go out. Right? You can go out because you have not used the the edge coming into going out, right? So and there are exactly 2, so therefore we can always go out. Now if you can always go out, then there should be some way to go out, right? But now since the graph is finite, this process must terminate at some point. But can it come back to one of these earlier vertices, right? In between, if that happens, then of course you see that this vertex has 2 incoming edges, right? So if there are 2 incoming edges, that is not possible because we said that every vertex has exactly 1 incoming edge and exactly 1 outgoing edge, right? Because we are looking at the bijections. Now, therefore, the only possibility is for this arc to come back to the starting vertex where we only use 1 edge, right? Only the outgoing edge. So therefore, this could be incoming, and hence we get 1 cycle. Now you throw away these vertices and continue with the remaining vertices. So again, you will get another cycle. cycle, so therefore you get a collection of disjoint cycles. So, so this we could do because the graph is finite, right? Otherwise, we cannot really argue in this way. Now, since every vertex has exactly one out degree and one in degree, the cycles that we have must be directed cycles, right? Again, why? Because once you go in, right, using the incoming edge, you have to go out using the outgoing edge. So therefore, if the process again terminates and it has to come back to the starting vertex, and therefore that must be a directed cycle. So these are easy things. Now, the same thing, so this completes the proof actually. And now, but we can prove it again using another idea that you just look at walks. So what you do is that you start from any vertex, let's say u. Okay. So you given this graph, you start from some vertex u. Now take a walk. You can take a walk because every vertex has one outgoing edge, so you go out, right? Now the walk continues, but since the graph is finite, the walk eventually must repeat the vertices. Now, when the first vertex that repeats must be the vertex u itself, because otherwise the repetition vertex, as we said, will have two pre-images. Now, because of this, we come back to the vertex and find the smallest k for which the vertex repeats. That vertex must be the vertex u itself, and therefore v1 to vk is a cycle. So again, continue with v minus the vertices we have already covered, and then you get decomposition. Now, here is an interesting homework question. So let C and K be the number of permutations of an n element set whose functional digraph is a disjoint union of k cycles. Okay, exactly k cycles. Now show that C and K satisfy the following recursion formula. So what is the recursion formula? C of nk is equal to C of n minus 1 comma k minus 1 plus n minus 1 times C of n minus 1 comma k for k strictly between 0 and n, with the initial conditions C of n0 is equal to 1 if n is equal to 0, and it's equal to 0 if n is not equal to 0, and C of n comma n is equal to 1. So these are the initial conditions, and then you can try to prove that C and K satisfy this recursion formula. Now we will come back to the C and K. This is an important number. We will come back and give it a name and etc. That we will do later. Now, another very important concept in graph theory and both digraph theory also is that of connectedness. Now, suppose you are given a graph or a digraph. We say that the graph G is connected and respectively strongly connected if and only if for every pair of vertices u and v there is a uv walk in G. Okay, so when I say for every pair of vertices in u and v there is a uv walk, so the walk must be there for vu also in the case of directed graphs, and in the case of undirected graphs it is automatic. So yeah, so here is an example of a graph which is connected. What is that? This graph, right? Because from any vertex to any other vertex, you can find a walk, right? So I can start from this vertex, for example, go here and go here. So these two are joined by a walk. Similarly, I can go all the way here and any vertex to any other vertex like that, right? So since this is possible, then we have a connected graph. Now this digraph is strongly connected because again you can verify that if you start from any vertex, you can go to any other vertex, right? So I want to go from here to here, here, right? This is possible. I can go from here to here. Similarly, from any vertex, I can basically go to any other vertex, right? I can go all the way back here, right? So this is possible, and if you verify all this manually for any two, this is possible, then we can convince that this is actually a strongly connected graph, strongly connected diagram. And when we say it is graph, we say connected, and otherwise we say it is strongly connected in case of diagrams. Now, here are some examples of graphs which are not connected, right? So here is one example of a graph which is not connected, because if I take any of these two vertices, right? Let's say give some names 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, right? I can go from 1 to 2 or 2 to 1, but I cannot go from 2 to 3, for example, right? Or 2 to 6 or 3 to 6. These are not possible. So therefore, these are this graph is not a connected graph. What about this digraph? Is it strongly connected? Well, I can go from this vertex, for example, to this, or I can go from this vertex to this, or this vertex to this, but I cannot go from this vertex to this, or even from this vertex to any of these vertices. So therefore, this is not strongly connected. What about this? This one is let us see. So I can go from here to here or here or here, right? I can go from here to here or here. I can go from here to here, right? Any of these vertices. But again, this is not strongly connected because I cannot go from this vertex, for example. I cannot go to this vertex or this vertex, right? There is no way to go there. Therefore, this is not strongly connected. What about this? Well, this looks very similar to this, but now in this case, it is strongly connected because I can go from this vertex to any of these vertices, as well as I can go from this vertex to any of these vertices, right? And similarly, I can go from this vertex to any other vertex because I can just go from here to here, and then go here, and go to any of these. So therefore, this is actually strongly connected, right? This is not strongly connected. This is not strongly connected. And this is not connected. So these things we can. Now, given a digraph, we sometimes look at the arcs as undirected edges. Okay, and then talk about the underlying graph. Okay, so when you have a graph, directed graph, let us just look at this graph, but don't look at the directions. So we will just consider that these are not directed edges; these are just plain edges. So then we get this kind of a graph which we call the underlying graph. It has the same structure, right? But the directions are not present. Right? So it's like the network is there, but we have not decided which one is like road network is there, which one is going to be the one ways are currently vehicles go in arbitrary directions, but then eventually once you decide this is what you want to do, then you can put the directions. So this underlying graph is an undirected graph, and this is sometimes useful to look at. So since we have this kind of a notion of underlying graph, we can also define another kind of connectivity, which is called weakly connected. So a digraph is weakly connected if its underlying graph is connected, right? So I can say that this graph is weakly connected, even though it is not strongly connected clearly. Similarly, this is also not strongly connected, but I can see that this is also weakly connected. So now we have two notions of connectedness in digraphs, right? That of the weakly connected and strongly connected. Now, here is something that you may have already observed, but homework for you to do, that graph G is or a digraph is given, then U and V are two vertices. Then there is a UV walk in G if and only if there is a UV path in G. Okay? Similarly, if there is a UV directed walk in G, then you can find a UV directed path, and if there is a UV directed path, of course there is a UV directed walk. Right? So prove or disprove this statement. Right? If one direction is immediately clear, the other direction also, if you can prove, then you can prove it, or you can try to disprove it. Now, given a graph G and a pair of vertices, let us say that U is interconnected to V. Okay, if there is a path connecting U and V. Okay, so U and V are interconnected if there is a path connecting U and V, and then we use this notation to say that the vertices are interconnected. Now, this defines a binary relation, right? Because two vertices are given, you can always check whether it is interconnected or not. Now, this relation happens to be an equivalence relation, and you should verify that it is true. The equivalence classes under this relation are called the connected components of the graph. Okay, so given a graph G, whenever two vertices are connected by a path, we say they are interconnected. And under the interconnection equivalence relation, the equivalence classes are called the connected components of the graph. So given this graph, right? So this entire thing is one graph. You can talk about the components of this, right? So what are the connected components? The connected components, or simply components, are basically this is a connected component, right? You can verify that these are all equivalence classes under this connectivity relation, right? Because because of transitivity, for example, right? So if this and this is in the same class, then they should be connected by somewhere, right? So therefore, this one by itself is a component. This thing is another component, right? And here you have this component. Now, one corollary, or one result that we can obtain from this definition is that the components are maximal connected subgraph. Okay. So, for example, what I wanted to emphasize is that this is a connected subgraph, right? If I look at these three vertices, just these three vertices, 1, 2, 3, right? Not 4, right? So just 1, 2, 3, if I take, then that is a subgraph which is connected, but it is not a component because it is not a maximal connected subgraph, because 4 I can add to this and it will still be connected. So therefore, this one by itself is not a component, but it is a connected subgraph. Now, given a digraph G, we can similarly define an interconnection between a pair of vertices U and V. But here we are saying that they are interconnected if and only if there is a UV path and also a VU path, right? Because directed paths we are looking at. Then again, in this case, the interconnection relation is an equivalence relation, and the equivalent class are called strongly connected. Okay? This is very similar to what the previous definition. So here is a graph, and let us look at the strongly connected component, right? So what are the equivalence classes under this? So you can verify that the subgraph including 10, right, 5, then 6, 4, and 11, right? This forms a strongly connected component, and it is a maximal strongly connected subgraph. Therefore, it's actually a component. And then what are the other components? Other components, for example, this 7, 8, 9. this is another component. Right? 7, 8, 9, you can verify that it is strongly connected, and it is not part of this large component, so this is a separate part. And similarly, the vertex 1 by itself is a component because it is not strongly connected to anything else. Similarly, vertex 2 by itself is a component, and vertex 3 by itself is a component. Right? 1, 2, 3 is not 4, 2, 3 is not a component, or 2, 3 is not a component. There is no way to reach 2 from 3. So these are the strongly connected components. Now, if you look at several examples like this, you will notice something else. So maybe it is a good idea. You look at several digraphs and look at the strongly connected components and see whether you can see some pattern. Okay, so some property. So now here is the property that I want you to prove. So let C1 and C2 be two strongly connected components of a diagram. Okay. Now suppose there is some edge between C1 and C2. Then all the edges between C1 and C2 are going to be in the same direction. Okay. So which means that either all the edges start from C1, right, vertices in C1, and end in vertices in C2, right, between them, right? Or like all the edges from C to go to C1, right? So the edges between them, that is what I am saying. I am not saying about the edges in C1 or C2, but the edges that connects between C1 and C2 are going to be all in the same direction. Now, more definitions. So given a graph G with vertex at V, let A and B are subsets of B. Now let X be a subset of the vertices and the edges. So X is a subset of B union E, such that every AB paths, right? So A and B are subsets. Now AB paths are basically paths with starting vertex in A and ending vertex in B. Okay? So look at any AB path, right? So every AB path, suppose it contains some vertex or an edge from this set X. Okay? So no matter which path you take from A to B, right? From any vertex of A you can start, and any vertex of B you can go, and you can consider any such available path. Now, if every path contains at least one of the vertices or edges in X, then we say that set X separates A and B. In the sense that if you remove X, right, then A and B are going to be not reachable from either, right? So B is not reachable from A and A is not reachable from B. Now, if X subset of the vertex set alone is separating, right? So instead of X subset of B union E, X is just subset of vertices, right? So a subset of vertices is separating, then it is called a vertex cut. Similarly, if a subset of edges is separating, it's called an edge cut. So these are just some terminologies that we will need sometime. Now, a cut edge or a cut vertex in a graph is basically an edge or a vertex whose removal increases the number of components of the graph. Okay? So, for example, if you look at this this graph, right? See, the edge E is a cut edge because if I just remove the edge E, the number of components in this entire graph increases to 3, right, from 2, right? So therefore, the edge E is a cut edge. Cut edges are also called bridges. Now, do you see any cut vertices here, or do you see any other cut edge? In fact, you can verify that E is the only cut edge in this graph. But there are several cut vertices. For example, the vertex A is a cut vertex because if I remove A, then it disconnects. It increases the number of components to 3 again, right? Similarly, D is a as a cut vertex. If I remove D, then you get the number of components increases. Okay. Similarly, C and B are also cut vertices. You can verify. So you can verify that these are precisely the cut vertices of this graph. If you remove any other vertex, it does not increase the number of components. Now, so here is a theorem. An edge of a graph is a cut edge if and only if the edge does not belong to any cycle in the graph. Okay. So how do you prove this? Now, if you delete an edge E, right? The deletion affects only its component, right? Because so if you are looking at different components of the graph, then deleting one edge from a component is not going to change the connectivity or number of components of anything else. Only that particular component will be affected. So therefore, without loss of generality, we can assume that the graph is connected, right? Because we can just do for each of the components separately and then put them all together, right? So therefore, we will assume that the graph is connected. Now, so given this graph G, so let us take some edge E of this graph, right? Let's say E is equal to xy. Now, when you look at G minus E, right? So if G minus E is connected, so suppose you have this graph that you obtained by removing the edge E. Suppose it is connected. So if it is connected, what are we saying? So if G minus E is connected, then that means that by definition there is an xy path, because every xy walk means that there is an xy path also, right? So by definition of graph being connected, there is an xy walk and therefore there is an xy path also. Now, so therefore G minus E has an xy path, but now putting the edge xy back, right? So x to y I can go, now y to x I can join, right? So the by the definition of the cycle, the way we defined, what we are saying is that you have, let's say, an xy path right in the graph. Now you add the edge xy, right? So therefore you get a cycle. So this creates a cycle, and in which E is a part, because I am using this edge E to make the cycle. So therefore the edge is part of a cycle. So if G minus E is connected, right, then E is part of a cycle. Now conversely, suppose that you have a graph G and there is an edge which is part of a cycle C. Okay. So we call the cycle C, and then we look at any pair of vertices in the graph, because the graph is connected. Any pair of vertices UV has some UV paths, right, in the graph G, right? So given any pair of vertices, say U and V, there is some UV path P, right? So there must be, right? U and V are given. There is always some UV path because the graph is connected. Now suppose the edge that we are looking at is not part of the path, right? Suppose E is not part of this path, E is somewhere else. Then deleting E is not going to destroy the connectivity between, right, interconnection between U and V, right? Because UV path does not contain the edge E, so removing the edge E is not going to affect the interconnection. So therefore, we will assume that E is actually part of the path B. Right? So suppose E is part of the path B, then so let us consider this arbitrary vertices U and V, and then we look at the path B, and in which the edge E is a part of. Okay, so this is the edge E. E is equal to xy. Now, what we know is that xy is the edge E or xy is part of the path B, right? So U to V path. Now, because this xy is in a path, either x has to come before y in the U to V path, or y has to come before x. By symmetry, we can assume that x is coming before y. So therefore, we have this ux path, then xy, and then y to v path, right? This is the whole path p that we have. So our path p is composed of the uv path, then the xy edge, and yv path. Right? Now, ux path means that u and x are interconnected, right? YV path means that y and v are interconnected. So I removed xy, but from the path p, ux is still interconnected using the path, and similarly yv is interconnected using the same path. But now we assume that xy was part of some cycle C, right? So since xy was part of some cycle, other than the xy, there must be another path from x to y. Right? That is the path of the cycle, right? The cycle was created by xy when xy was added to the x2 y path through the cycle C, right? So you had this cycle C. So through C, x and y are interconnected, right? Even though x and y edge is not there, x and y are interconnected through the path. Now we already know that ux are interconnected. We now show that xy are interconnected and yv are interconnected. But interconnection relation is an equivalence relation, therefore it is also transitive. So using the transitivity property, we see that u and v are also connected in G minus E. So therefore, the result follows, right? So we proved that an edge of a graph is a cut edge if and only if it does not belong to any cycle in the graph, because it cannot separate if it is is part of a cycle. Now, another very important notion related to what we are looking at is that of k connected. So a graph is said to be k connected, right? If g minus x, right, x is some vertex set, is connected for every subset of v whose cardinality is strictly less than k. Or in other words, what we are saying is that a graph is k connected if by removing less than k vertices, the graph cannot be disconnected. Right? So no matter how many vertices I remove, right? As far as the number of vertices that you remove is less than k, no matter which vertices I remove, if I remove less than k vertices, the graph will still be connected. And the largest k for which the graph is k connected is called the vertex connectivity denoted by kappa of G. Okay. So kappa is the vertex connectivity or simply connectivity. When we say connectivity, it is usually the vertex connectivity. Okay. Kappa of G is the largest k such that G is k connected. So so if you take kappa plus 1, right? If you can show that, like, removing kappa vertices, the graph will be disconnected. You can find some subset of kappa vertices which will disconnect the graph. So here is two graph. Here are two graphs, and look at the vertex connectivity, right? So in the first graph, you can see that the vertex connectivity is 2, because if I delete, let's say, these two vertices, right, then the graph becomes disconnected, because there is no path from this part to this part. This graph, it's one connected. Connectivity is 1 because if I just remove this vertex, it's a cut vertex. In other words, if I just remove this one vertex, the graph becomes disconnected. So in this graph, there is no cut vertex, so the connectivity is 2, and here there is a cut vertex, so connectivity is 1, and the graph is connected also, right? This and entire part. But suppose I added something like this, right? Then the graph is not connected, so the connectivity is not 1, right? It is 0. Now, similarly, we can define edge connectivity. So a graph is L edge connected if G minus F is connected for every subset of F subset of edges with cardinality less than strictly less than L. So by removing less than L edges, you cannot disconnect the graph. Then it is L edge connected. And the edge connectivity lambda is the largest L for which G is L edge connected. So here are some examples, right? So we have this graph, right? So what is the edge connectivity? Well, you can verify that by removing one edge or two edges. You cannot disconnect the graph. But if I remove these three edges, it becomes disconnected because this vertex and the remaining part will not be connected. So therefore, this is edge connectivity is 3. You can verify that. On this graph, for example, the edge connectivity is 2 because I can just remove these two edges. It will disconnect the graph. And no less than 2 will disconnect the graph. Again, we have to verify that manually. What about this graph? Well, this graph, the edge connectivity is 2 because I can either remove these two edges or I can remove these two edges, which will disconnect the graph. And but if you remove just one vertex, the graph will be disconnected. If you remove this vertex, this and this will be separated. Now, what about this graph, right? What is the edge connectivity of this? So if you look at this, it is not immediately clear, right? But if you go through it very carefully, you can verify that the edge connectivity is indeed 2 in this graph also. Okay? Because if I remove these two edges, right, you can verify that the remaining graph is not connected. These are just superimposed on the other similar path. So therefore, the graph is really only 2 connected. Yeah. Now, if you look at more examples, you can see something that the vertex connectivity is going to be less than or equal to edge connectivity of the graph, and the edge connectivity is going to be less than or equal to the minimum degree of the graph. So this is something that you can see by looking at examples. Now the question is that why this is true. So maybe you can think about this and try to give a proof. So I will say that this is a good homework. Okay, so vertex connectivity less than or equal to edge connectivity less than or equal to minimum degree. Now, very important notion of graphs, which are called bipartite graphs. Okay, so we earlier defined an independent set is a subset of vertices where there are no edges between them. Now, if you can basically partition the vertex set into 2, right? So disjoint V1 and V2, such that V1 and V2 are independent sets, then we say the graph is bipartite. So here is an example. So if you look at this graph, right? So let me look at the vertex set and put it into these two sets. Now these two sets, right, are independent because there is no edge between any two of them between themselves, right? So there is no edge here, 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 here. Similarly, this is also an independent set, right? Within that subset, there is no edge between them. So therefore, you can decompose the graph into two sets which are both independent, and it covers all the vertices. Therefore, this is called a bipartite graph. Similarly, the graph represented on the right side, this is also a bipartite graph. You can verify this by defining an independent decomposed into two independent sets. So what are these? So just look at the odd numbered vertices, put it into one set. Look at the even numbered vertices, put it into another set. You will see that they are independent, right? Because if you look at the odd vertices, right, 1, 3, 5, and 7, right? There are no edges between any two of them. Similarly, if you look at the even numbered vertices, 2, 4, there is no edge between 2 and 4, 2 to 8, 2 to 6, 4 to 6, right? 6 to 8, right? So, yeah, so you can verify that that is also an independence. So you basically decompose the graph into two independent sets, and therefore it's bipartite. Now, a very important theorem, a graph if G is bipartite if and only if G contains no odd cycles. Okay, no cycles of odd length. So all the cycles in G must be, if there are any, must be all even length cycles. Now, how do you prove this? Well, one direction is immediate, right? Because suppose the graph is bipartite, then it cannot contain any odd cycle. Why is that? Because suppose you want to look at cycles, right? So if there is a cycle, you start from some vertex, right? Then go through a walk, right? Without repeating vertices or edges, and then come back to that vertex, right? Let us look at any walk from this vertex, right? Any walk from this vertex is going to alternate the sets x and y because there is no edge between x. I have to go to y first. Then, since there is no edge in y, I have to come back to x again, right? Then I have to go to y, right? Then I can come back to x again. So therefore, anytime the path comes back to itself, right, to the same starting vertex, or in other words, the walk is a closed walk. It is of even length because I have crossed this bipartition exactly an even number of times. Now I go to the right and then come back. Again go to the right and come back. So since every closed walk is of even length, you cannot have odd cycle because if there is an odd cycle, you can just trace the cycle, come back to the same vertex, and you get an odd walk because we just proved that every closed walk is of even length. So therefore, one direction is clear, right? So let G be a bipartite graph with bipartite in xy. Starting from any vertex, every walk alternates between x and y. Thus, to return to the starting vertex, it takes an even number of edges. So therefore, G cannot have any odd cycle. Now, the other part, right? The conversely, suppose you want to prove that a graph is bipartite if and only if it has an odd cycle, right? So suppose there is no odd cycle, then you have to show that the graph is bipartite. So how do you show that? So we take a graph without any odd cycles and then we construct a bipartition. So what I do is that we start with any component of the graph because if there are several components, I can find bipartition from each of the components and then put them together, right? So let's say that there is this component, I have a bipartition. Another component, I have another bipartition, right? Then another component, I have another bipartition, right? I can put these bipartitions together, right? And then I can say that because these are all independent sets, there is no edge between them. This is an independent set, similarly this is an independent set. So I can get bipartite graphs if I have a bipartition for each of the components. So we will just work with one of the components and show that how I can give a bipartition for this component. So what I do is that I start from the vertex some fixed vertex, let's say v or u, right? So I start from a vertex u, and then for any vertex in this component, right? Every possible u to v walk has the same parity. That is my claim. Okay. So I start from a vertex u, and then I take let's say some vertex v, right? Now the claim is that every uv walk has the same parity. Right? Now why is this true? Yes. So what I'm saying is that if I can find a walk from u to v of odd length, then every walk from u to v is of odd length. Similarly, if there is a walk from u to v of even length, then every possible walk from u to v is of even length. Why is this true? Okay, so think about this. So here is the argument. Suppose let's say that W1 is a UV walk of even parity and W2 is a UV walk of odd parity, right? The length is odd in one case and in another case it is of even length. Now these walks could be could be non-intersecting walks, or it could be intersecting walks, right? So because I am talking about all possible walks, right? So maybe you have this kind of a situation, right? U to V through W1, U to V through W2. This is of odd length. This is of even length. Now similarly, you can have U to V like this, but the which is even length, and then there is an odd length path. Goes through this. It basically crosses over and uses some parts of W1, right? But again, finally reaches V. Suppose this is of odd length, right? So any of these cases is okay, right? So suppose you have these walks. So now if I have a UV walk, so I also have a VU walk through this path, right? So I can go from U to V taking the even path, and then V to U I can take the odd path, which is W2. Now if I can do this, then I get a closed walk. But the length of the closed walk is even plus odd, which is odd. Now, if you remember, I asked you to prove that if you have an odd walk, right, a closed walk of odd length, then it must contain an odd cycle as a subgraph. Now, it doesn't matter whether the walks are intersecting or not. We never use the fact that they are intersecting or they are disjoint, right? But we just said that okay, U to V I can go taking a walk, and V to U I can go taking the other walk, but they could intersect. Doesn't matter. But it is still a closed walk and it has length odd. So therefore, using our result that every closed walk of odd length contains an odd cycle, you can show that there must be an odd cycle here. So therefore, our claim must be true that every UV walk has the same parity, because if it is different parity, then you can add them together to get a odd closed walk. No, so therefore, so this is the restatement, right? So we get a UVU closed walk by reversing the walk W2 of odd length, which is of length W1 plus W2, and a closed walk of odd length contains an odd cycle. So this is a homework question that I gave you before. Now, using this fact, let me define a bipartition of the component H that we are looking at. So what is the bipartition? Collect all the vertices of H where the UV walk has even parity, right? Because every vertex has either odd parity or even parity. So put all the odd parity vertices in one set and all the even parity vertices in another set. So the even parity vertices forms V1 and odd parity vertices form, let's say, V2. So for this component H, now we have covered all the vertices, because every vertex is reachable from every other vertex. So from U, every vertex is reachable because the graph is H is connected. So now, since we have this partition into V1 and V2, we have to just verify that V1 and V2 are independent sets. Right? Now, suppose V1 and V2 are not independent. Is it possible? Well, let us take let us take the case. Let's say that you have this U, then you have let's say V1, and then you have V2, right? Now, no. What I want to say is that this is small V1 and small V2. Let's say these are maybe I should draw it in a different way. Let me draw it in a different way. Suppose you have the bipartition, let's say V1 and then V2, right? And you have some vertices, right? Now the claim is that V1 and V2 are independent. So let us say that one of them is not independent, let's say, right? Or both, doesn't matter, but one is not independent. So let us say that this set is not independent, which means that there must be some edge here, right? So there is some edge here. Now if there is an edge here, then you know that you have this vertex u from which we define the bipartition. So which means that u2, this one of these vertices, let's say x, and the other vertex y, there were some walks, right? But now because both of them are in the same component v2, right? So some same partition v2, then u2 x and u2 y must have the same parity, right? So therefore this walk has same parity, this walk also has the same parity. Now if I add the edge xy, right, so I can go from u to x, then go to y, and then y to u, which will create an odd closed walk because u to x and u to y have the same parity, so therefore adding them you will get an even number. Xy is 1, so therefore the length will be totally odd. So therefore I get an odd cycle, which says that it must contain an odd cycle, right? The graph must contain an odd cycle. So therefore this is not possible. So if x, yeah, so here a nice figure here, right? So starting from u, I had ways to go to x and y, which are of the same parity. Then xy edge makes it an odd walk, which is close, and therefore I get an odd cycle. So therefore this cannot be happening. So therefore xy edge is not present, right? So you cannot have an edge xy. So therefore we get a contradiction, and that says that v1 and v2 are independent sets. Okay. Now here are some more questions. So let G be a graph and P and Q be paths of maximum length in G. Okay, so we have two paths of maximum length in G. So that P and Q must share a common vertex. Okay, so any two paths of maximum possible length, right? They are having the same length. In G, okay. So I have to make a small correction here. So let G be a connected graph, and P and Q be paths of maximum length. So that P and Q must share a common vertex. So that is the first homework. Then let G be a graph, and P, Q are again be a connected graph. P, Q, and R be paths of maximum length, all of the same length, the largest possible length in the graph. Then there is a vertex common to P, Q, and R, like all of them pass through the same vertex. So you prove or disprove this. Okay, so that is the second question. Then suppose W is a closed walk that contains no cycle of G, then show that an edge occurs twice in succession in W. Okay. So you have a closed walk, and this walk does not use any cycle, right? Then show that an edge occurs twice in succession. Now, fourth question is that given a graph, that is a G, and some vertex X. So suppose the vertex X is a cut vertex in the graph G. Okay? So X is a cut vertex in G. Then show that in the complement, right? So complement is the graph obtained by making all the non-edges as edges and edges as non-edges, right? So show that in the complement, X is not a cut vertex. So you have a graph in which you have a cut vertex. So that in the complement of the graph, this vertex is not a cut vertex. Fifth question, let T be a closed trail in a graph G. Show that T can be decomposed into edge disjoint cycles. And finally, a graph is connected if and only if for every partition of the vertex at V to non-empty sets, there is an edge with endpoints in both the sets. Okay, so you have to prove this. So this is basically the homework assignments. Okay, so with this we stop for today. We continue in the